Okay, so welcome to the lecture, third lecture of this series on reflectance spectroscopy for characterization of rocks and minerals. I am Chattoraj from Geosciences Department, Indian Institute of Remote Sensing. So very good afternoon to all of you, and if you are outside India, so take my greetings as per your time zone. To start with, I'll first give you a glimpse of what are the theories behind this. How do I get the reflectance spectra of rocks and minerals? What are the physics behind that? And then we'll take up a few case studies, both terrestrial and from planetary samples. So, as you know, what I understand that you must be knowing about what reflectance is. So, reflectance is basically the reflected energy that is coming out from the surface of a geophysical matter. Now, so the reflectance will be the energy that is coming out divided by the total energy that was impinging upon that. So, as we know that the energy what was impinging may be absorbed, may be emitted, may be reflected. So, the reflected part of that is of our interest, and as you see here, the reflectance properties of rock forming minerals, especially if we consider the rock forming minerals only. So that is a function of chemical composition and the crystal structure of the diagnostic spectral absorption features. So that is basically the chemical composition and the crystal structure. Both will have a role to play. So the chemical composition of the mineral, that means the chemistry, the constituent cations, anions, and the crystal structure. So crystal structure is basically what type of mineral it is. It is a tetrasilicate, or it has a three-dimensional structure, sorosilicate. What type of silicate it is? What about the bonding strengths? So all these will matter. So that is basically physics-wise, the photons are absorbed in minerals by the processes, several processes. Out of that, the absorption process and the wavelength depends upon the dependence allows to derive information about the chemistry of the minerals from its reflected or emitted light. But emitted light, as of now, we are not considering. We will only consider the reflected one. So process-wise, there are few processes have been jotted down. First is electronic process that we will discuss here first. So here from this process we get absorptions in visible to near infrared region. So 400 to 1000 nanometer is where we are focused upon, and they are generally associated with the electronic transitions that caused by the presence of transition metals like iron and chromium. So iron, chromium, these kind of metals, they have their last orbital electron, they are free, and so that's why they can move, and depending upon the impinging energy, so they will produce some kind of reflected energy, and this reflected energy is visible to us in terms of different colors. So that's why basically we see red coloration for iron bearing minerals. So basically it has to do with the presence of iron, and the color that is reflected is in the red spectrum. So that's why the color is red. There are several subdivisions in this electronic process. One major important is the crystal field theory. So crystal field theory, CFT we call it, that basically deals with the transitional elements, D block elements. So there are different, electronic cell structures, if you see, and then we know SPDF, the electronic cell subcells. We have a certain number of electrons that can be there with different spins. So whichever is having this D block electrons, so they are called D block elements. They have unfilled electron. So unfilled electron within that cell. Where it can happen in nickel, chromium, cobalt, iron, and then splitting of the d orbital energy gives generates some kind of forces, and this basically makes the electron to move to from a lower to higher energy state by absorbing the photon from the impinging energy. So the moment the electronic state varies, so the electron goes from a lower energy to a higher energy state, it basically radiates some kind of energy, and this energy that is either absorbed or being radiated. So that is reflected as an absorption is your reflectance curve. We'll just see how the reflectance spectra looks like and what the absorptions mean. We'll discuss there. But as of now, we have to understand that the electrons are moving from lower to higher energy state due to absorption of impinging energy, absorption of the photon. And so that's how they are getting agitated. And because of this agitation, the energy changes in their different electronic cells, produces a kind of energy. And this energy perhaps is, we can catch that, detect that using our instrument. So the CFT crystal field basically depends upon the mineral structure, that is in turn that is the valency state of the atom, which valency state is coordination number, the symmetry of the site, if it is a octahedral, tetrahedral site, and what about the symmetry, the type of the ligand it forms. So it's a metal, and then inorganic ligand is basically a complex organo chemical structure. So they are attached to your anions sometimes. So that they become there exists a bond between the cation and your ligand. So depending upon what type of bond, what type of ligand they are, and the extent of the distortion of the site. Sometimes it happens that the original structure will not give any kind of response, but if it is distorted by some means, then the distorted structure will give some kind of will show some kind of CFT crystal field effect. Then metal ligand interatomic distance. So all these taken together gets me what is called crystal field. So if I try to understand the basics, very basics of VNIR, by this time we have learned about the crystal field effect, that is because of the electronic transition process, and we'll see what are the results of this crystal field. So this is the reflectance curve, and this side is my wavelength region. So wavelength 0.3 to suppose 0.4 to 2.5 we have plotted this way, wavelength, and this is this axis, y-axis is your reflectance axis. So reflectance, again I will tell you is the energy that is reflected by the impinging total energy. So if more energy is being reflected back, right? So suppose 100% is received and 100% is again reflected. So there is high reflectance, that will be close to 1. Otherwise, if it is low reflectance, very low, so if it is all the impinging energy is being absorbed, so then nothing is being reflected back. So that means my numerator will be 0. So that makes my reflectance 0. So reflectance can vary from 0 to 1. And if we see the variation of this reflectance along this axis, wavelength axis, we get this kind of line. They are called the spectra. Spectra, that is basically a manifestation of how the reflectance quality varies, that is coming up from a surface. So suppose the surface is mineral pyroxene here. So from the pyroxene you are getting this reflectance, and you see there are some highs, there are some lows. So these lows are my absorptions. Generally, we do not consider these highs, but lows are very much important. So what we do here, the lows basically we see where it is happening, the wavelength, which wavelength region. Like here, suppose it's happening at 0.9. So this 0.9 we'll call a band. So the moment I call a band simply means that there happens an absorption. So this absorption is basically happening in your this at 0.9 micrometer. So 0.9 band, micrometer band is what we call it. Then suppose here it is 1.8 micrometer band, another band. So this is more broader than this, and this is more symmetric. This is slightly less symmetric. So this pyroxene is characterized by, in this graph, by these two bands. So the moment we get the reflectance, these reflectance bands here, we know that this is because of the pyroxene mineral. Now the problem that happens with nature is that we do not get a spectra from a single mineral. It never happens. It may happen if it is a monomineralic rock, as all of you will be knowing. If it is a monomineralic rock, that means that it is made up of only one type of mineral. So you can get a structure like this. But the moment we get, generally there's a mixture of the minerals, so the moment we get a mixture, then we start getting a mixed spectral response. So how the mixed spectral response will look like? So that is a matter of concern, and obviously you understand that the more predominant the phase is, its influence will be more on the resultant spectra. So that's it. So you have to be, you have to open your eyes, and you have to observe that this is a mixed spectra or a single spectra derived from a single mineral. So most of the time it is a mixed spectra, and if it is mixed, then suppose we have this. Look at this spectra where we have olivine and pyroxene in different varying proportions. So olivine 20% and pyroxene 80%. Suppose we take 1 gram of sample, 100 gram of sample. So within that 20 gram by weight olivine we have taken, and 80 gram of pyroxene by weight we have taken. We can go by volume also. So 100 cc, then 20 cc is your olivine, 80 cc pyroxene. So both volume and weight wise we can mix it. So olivine is to pyroxene 20-80. From that we can go up to 80-20. So all possible combinations. Suppose here we have taken 3 possible combinations, and you see the difference between these two. So the moment olivine predominates, please see this is the green curve. So green curve, there's a band shift. If you call this 0.9 as band 1 and this 1 point close to 2, suppose is band 2, close to 2 we get a band 2. Now please see what happens. The moment the color is green, that means if olivine is more, olivine is 80%, then the band 1 basically shifts from this position to this position. So what I want to look at here is the absorption minima. So where absorption minima in blue line was happening exactly here, now the absorption minima has shifted onto this place. So this much of shift happens. So as we are plotting 0.5 to 2.5 here, so it's not that prominent, but if suppose we just modify the axis in a way that we rescale it so that 0.5 is here and 1 is here. So you will be able to see very conspicuously how much is the variation. Similarly, band 2 also, there are subtle variations. See, with olivine enriched, what is happening, if my band 2 absorption minima remains fixed at a particular wavelength, if it is fixed, but what is happening, the depth basically is decreasing. So depth from this shoulder, if I take, so for the blue line, blue spectra was this much, and for green line, please see how much the depth remains. It is decreasing. So depending upon that, depending upon the constituent minerals, both your band position may shift, and it can have an influence upon your band depth. So band depth also it can influence. So what is happening here? The position. What are the diagnostic parameters? The position of the absorption features is a function of the crystal structure that we have understood till now. The intensity of the features is related to the abundance of the absorbing phase species. What is the absorbing species here? Iron. So we have just now discussed about the crystal field theory that is mainly manifested in minerals like iron, chromium, nickel, etc. So iron is the absorbing species, and then if it is absorbing, it produces band 1 and band 2 absorption in your standard spectra. But that will be that is a function of the mineral and the mixtures. So they are basically related to the abundance of different minerals. The moment you go to another phase, 20-80 to 80-20, your band depth and the absorption depth both changes. Okay. So these are common minerals and their band positions that has been marked here, and which cationic site this cation, the absorbing species, is housed in which cationic site, that is mentioned here. These are commonly spelled out sites, cationic sites that we read in crystallography. So suppose we take one magnesium silicate, so MgSiO3 if I take, pyroxene if I take. So that pyroxene Mg will go to M1 site or M2 site, depending on that we have read. So these are the common sites and the common cations that because of this presence of this only the bands are happening, and where they are supposed to happen. They are the common bands. Right. This is what we have been discussing. Suppose we even in a single mineral phase like olivine may appear as a single mineral, but perhaps it is not. So olivine is a solid solution. It produces a solid solution series. So in that solid solution series, we have the variation of Mg and Fe. So one member, suppose, is Mg rich and another is Fe rich. So obviously, both these type of olivines will show my shift of 1 micrometer band absorption. So the moment it goes to your phyllite rich, iron rich olivine, or it goes to your phosphorite rich olivine, then magnesium rich olivine, then there will be shift of this absorption minima. So that shift basically, however minute it can be, that shift is basically very much important to identify that particular mineral. Not that particular mineral, it will help you even dig further and tell, it will be able to tell you that which particular solid solution end member it is. So within the your olivine series, where exactly it is phosphorite or phyllite or in between something, you will be able to tell. Right, so this is how in pyroxenes, olivine, now in the pyroxene, how the bands will vary. Now we come to the other process where there is charge transfer, where there are conduction bands and there are color centers. All of them are electronic processes related to electronic processes only. So charge transfer, where the charge basically is transferred to another phase. Conduction image, some elements are designated with two energy levels, already two energy, lower energy level and higher energy level, like the sulfur. So they basically show the conduction bands and the color sentence. So even if you do not understand, if you do not know that by what physics, because of what physical phenomena it is happening, but at least you have to know that where does my band happen and due to which particular element it is happening. So these two are of utmost importance if you have to characterize or if you have to get to know what particular mineral it is. Now coming to another very important phenomena that happens with spectroscopy is vibrational theory. So vibrational theory also is that is manifested by many important rock forming minerals, which basically where the cations are your hydroxyl, NH2O or carbonate. So these kind or carbonate, hydroxyl, or suppose there can be a metal oxide or hydroxide bonds. So L, O or OH, and then magnesium Mg, O or OH. So magnesium oxide, magnesium hydroxide, aluminum oxide, aluminum hydroxide. So these kind of metal oxide or hydroxide bonds. The first, second is your carbonate. All your carbonates basically will come under this, and then your OH, so hydroxyl, water bearing. So they also are basically shown due to the vibrational process. What this basically is that if you take a standard spring, you attach it to something and then give a weight here, and then it basically produces a kind of motion. So they are vibrational motions. So vibrational motions, there are different kinds of vibrational motions. It can be simply one fundamental motion, so that is the most prominent one. It can be your overtones. So overtones basically that happens that do not coincide with your fundamentals, and there can be a combination of these two where both of these occur together, so that can be your combination. So combination of overtone and fundamental, these three basic type of vibrational features that happen with all these kind of minerals. So here you basically get vibrational spectrum absorption due to vibration, where in hydroxyl, in carbonate, in phosphate, all of them it happens. So most of them, please look for this, they are anions. So earlier CFT, crystal field, if you see, they are mostly cations. Here we're talking about the carbonate, CO3 2 minus, hydroxyl 1 minus, then your phosphate, then your metal oxide or hydroxide bonds. So these all are your anions mostly. Right, so we have to know that where exactly, suppose Fe was happening at, suppose the earlier described band 1 and OH H2O, that is very interesting. So generally 1.4, 1.5 you get your OH, and then around 2 you get your NH2O. So water bearing, typical water bearing, this is hydroxyl bearing. So if in a spectra, if only 1.5 is present, so you have to designate it with hydroxyl, OH minus, like it happens with suppose ampivols. So ampivols in last, if you see the formula, common formula, you get OHF, right? So in the last phase you write those. So if OH singly is present, so that you get at 1.4. If 1.9 it is happening, it can happen due to OH and due to presence of NH2O. So again, your hornblends like minerals like that, they have your NH2O also. So water is present, water in molecule phases is present there. So similarly, in different other minerals also we have the presence of OH and NH2O. Okay, so mica is a rock forming mineral and is very important. So in most of these minerals you get a kind of aluminium or magnesium. This aluminium and magnesium, they happen in the crystal bonding, they have to go with oxide or hydroxide. The moment they go with oxide hydroxide, so you get something at 2.2 micrometer, it happens, you get a absorption, and from this you can get to know that there are magnesium aluminium, so it can be a mica. And additionally it contains OH hydroxyl, so you see at 1.5 close to 1.5 there is a absorption happening. But if these are all your spectra that you are taking from the sample, right from the sample. If you are taking an image spectra, there is some water band that is available in the sky. So what happens in these regions, when light was coming or going back, when it is going back, reflected energy and going back to the sensor, so what you get is a reflectance image. In that image you get this 1.4, 1.9. You are not sure that they are because of simple water vapor absorption or they are due to the presence of the mineral. So you have to filter those out, then get to know that exactly the features are due to presence of my OH or hydroxyl bearing or NH2O bearing minerals. So that's how we have to be little cautious. But if you are taking spectra using your spectrometer, handheld spectrometer, you always know, you always sure that they produces your oxide or hydroxyl NH2O producing bands are there. Yeah, this is one typical reflectance graphs that we have seen in many standard books. So let us start with this hematite. Hematite is iron bearing oxide. So what happens? Iron, because of the presence of iron, please see you get this 0.9 micrometer band. So this is never missing band in hematite. And what happens is that people say that if it is handheld spectra, that is okay, but if I'm doing with the image spectra, so reflectance energy is going back and the image catches that, and we in our computer we see a reflected reflectance image. Now within this reflectance image, suppose the spatial resolution of this the image is 30 meter. So spatial resolution, by now I assume that you people will be knowing what spatial resolution is. Simply taken, the spatial resolution is nothing but, suppose we are seeing down and then we see two objects are at a distance more than 30 meter. So 30 meter ground spatial resolution simply means that if they are closer to 30 meter, they will appear as a single object. If they are at distance more than 30 meter, they will appear as two separate entities. So if spatial resolution is 30 meter, that means that is a 30 meter by 30 meter grid, one pixel. So that means on ground that is 30 meter by 30 meter. Now all who geologists or who study geology, they know that 30 meter by 30 meter continuous coverage of due to hematite seldom only occurs. You have to go to a hematite mine for that. So 30 meter by 30 meter, this square, if you have to get only hematite, is not possible. So there will be mixture, there will be other minerals, other rock types, it's highly possible. But I tell you, the beauty of this, the one 0.9 micrometer that happens due to the crystal field effect, as we have discussed earlier, the beauty lies in that they are basically, the iron may be in very minor amount. So even if that is present, this band is never missing. So you start getting 0.9 the moment you have some iron at least in that. So you will be able to tell that iron is present or no. So it is so conspicuous. It's like, you add impurity and that changes the whole substance. It's like that. So impurity may be very minor amount in volume or by weight. But if you mix it, it is able to change the color of the whole medium. So it's like that. So that's how we catch iron. Then see the montmorillonite. This is a smectite group of clay minerals. So in that, what we have, smectite basically gives me one hydroxyl, one NH2O, and then there are magnesium aluminum. So you get spectra absorption here also. Please see the orange one. So montmorillonite. Then coming to kaolinite, another candide type of clay minerals. Kaolinite are slightly simpler than your montmorillonite clays. Montmorillonite is smectite, so you have to have NH2O in interstitial spaces. So intercationic spaces you have NH2. That's why they are expanding clay. But this expanding nature is not there in kaolinite. So kaolinite is a simple structure. And please see, you do not get this typical NH2O, big NH2O, what happens in montmorillonite. Here it is diminished. But you again get a hydroxyl. So hydroxyl is there, but that much of NH2 is not there. But again you get a stronger 2.2. So that means you have some magnesium, aluminum, hydroxide or oxide bonds in kaolinite. Now, please see the black one, the orthoclase feldspar one. Orthoclase feldspar, what will happen? You get a completely flat line. So that is the beauty of this. Any tectosilicates or three-dimensional structures where, like your quartz, like your feldspar, they are one of the most prominent rock-forming minerals. But unfortunately, if we see in this range 0.5 to 2.5, we get a flatter. There is no absorption at all. So it's very difficult to characterize, detect this. But again, if it is in conjunction with other, the flatter nature is able to tell me that they are because of quartz or feldspar. Because otherwise, I would have got something like this. So that way, so no information is also a kind of information. Again, now coming to the calcite kind of group of minerals, carbonate. So what happens? Carbonate, suppose it's iron-free carbonate. So after this, we do not have anything. Then we start getting this 2.3. This we have not discussed till now. 2.3 carbonate band is very prominent, and it will happen with all your carbonate. You name it, aragonite, dolomite, calcite. It will happen. So that is a never missing band. The moment 2.3 is present, you should be akin to tell that carbonate is present there. Which phase of carbonate? If you study it further, there are research papers available that will be able to tell you, no, this is dolomite or this is calcite. There is magnesium, there is more calcium. So like that also people are able to tell that. And nowadays the spectroscopy is more equipped with many integrated things like integrated band depth. So band depth, not only one band we will consider, simultaneously we will consider many bands, two adjacent bands suppose consider, and then the normalized value of that is what we see as a characteristic feature. So many advanced techniques are also there to get you onto detection of the mineral. So there is a simple chart where it tells you that what are the common rock forming minerals and what are the absorptions that you get here. So and absorption type, what type of absorption feature you generally get. Now we have told about what happens with spectroscopy, what are the advantages. As for the limitations also, we need to know what we cannot do with reflectance spectroscopy. And then that part perhaps takes me to other type of spectroscopy like emissivity spectroscopy. So reflector spectroscopy, what are the limitations? Spectroscopy is unable to detect the minerals which lack diagnostic features like your quartz, feldspar. We have discussed that quartz or feldspar group of minerals, they basically lack a feature, and then that's why they are not detectable. Second is spectroscopy has limited capabilities of weakly featured minerals, where of the minerals whose features are obscured by interfering species. There is something that basically obscuring that, and you are misled often. So that basically is a problem. And then spectroscopy samples on a thin surface layer. So what lies underneath cannot tell you. It's only the surface feature. Again, it has its surface alteration processes are there. Alteration or chemical weathering features. They often lead to the different spectroscopic nature. The moment I say different, so they may not be characteristic for one particular mineral, but at the same time, if it is different and the difference is known, is standardized, has been documented, they are helpful in detection of alteration process. We will discuss in detail about this. So they are basically your common limitations. Then a thin surface layer, especially in terms of planetary surface, which are basically very old surfaces where regolith will be there, right? Where weathering suppose keeps on happening, and then until unless it is a fresh surface, so what you get the spectroscopy. If you have an onboard, suppose there's your reflectance spectroscopy sensor, so what it gets in return is basically the property of the thin layer, so regolith, not the actual rock. So that's why these are the your limitations of spectroscopy. Now coming to the advanced applications of spectroscopy, whatever we have learned till now was the basics of spectroscopy. What we can do with this? One is simply that identification of the minerals and characterization of the rock thereby. So that is one thing. Again, if I stuck with one particular mineral, I'm done. So what I have to do, I have to see the assemblages. Detection of one particular mineral may be misleading. You may be deceived. But if you simultaneously, if you are seeing a mineral paragenesis consisting of A, B, C, D, E, 5 type of minerals, so identification or characterization of those 5 types of minerals simultaneously cannot go wrong. So that's it. So that's why while studying the rock alteration, look for the mineral paragenesis. That simply means instead of one, you look for a paragenesis, number of minerals. So as we know that if something process ore formation process like hydrothermal process happen, and that basically bakes the country rock. So it's a hydrothermal fluid vent. So it's coming with hydrotherm means hydro means water and therm means your temperature, hot water basically. It is coming from down below and it has scavenged different metals from the surrounding rocks, and then it is coming onto the surface. So this hot liquid, suppose a granitic magma at the late phase, which is a silica potash rich phase, it is coming out to the heat just below the surface. And my country rock is a carbonate type of rock, and the phase that is coming granitic late phase, so that is rich in silica potash. So basically, what will happen? There are two things that will happen. First is that the temperature, basically, your ambient rock is basically heated by the temperature. So there can be a geochemical change which is due to the temperature change. So the adjacent minerals, the original minerals, they may be changed due to the temperature. So if temperature is there, then there will be metamorphose. So meta is at least, and some different minerals will be there. But as because it's a closed chemistry, closed geochemistry, so their composition, their whole chemistry, geochemistry as such will not change. But what happens if the hydrothermal fluid that is coming is enriched in different cations, and if it is enriched in ions like silica, potash, late phase enrichment. So that basically also come into the contact with that, and through different fractures or avenues, it intrude the country rock. And then the system is not closed, so there can be change in chemical composition also. Newer minerals start coming, right? So that's the beauty of this, and there are different zones. If this zone is considered as a host core region, core means directly beneath this was my hydrothermal intrusion. So obviously this is the maximum baked portion which supports the maximum temperature, and if you go away from this, the temperature effect basically dies out. So depending upon that, we get 4 different zones: potassic, then phyllic, argillic, and propylitic zone. The potassic zone is this zone which is the core region, which is rich in metasomatism will happen, and NS and CA phase will be leached out. Philic is important because the feldspar that was produced here, that basically changes to mica rich phases. So next phase is mica rich. Last phase next to this will be argillic. It's a clay rich. So all your mostly it will be dominated by your clay type of minerals. Then you have your lime rich phases or prophilitic. So depending upon that, you get different zones. It may not be possible in nature that even if it is hydrothermally altered, it's highly possible that you do not get the whole sequence, all 4 sequences in totality. So if you are studying a reflectance image that is born from the sensor, suppose, and the reflectance image you in your coming days or in this series, or you have already learned, you'll see that how to get different end members or different pure mineral pixels from your satellite images. So suppose by doing that, you know that these are the assemblages, and you can tell that no, we are this XY, we are basically within the philic zone. But what to do with that? So what beyond this? So characterization or hydrothermal alteration zone is okay, but what we can do with that? We can simply let ourselves know that where is the mineralized zone. Most of the mineralized that happens in this boundary. So where your maximum baked region is happening, the boundary of this zone is where you get maximum pores associated, maximum pore enriched. So you know which exact direction you have to walk to get the maximum zone of mineralization. Zone of mineralization, if you have to get, which way where should you put your drill spot? But you know, you never know that if that all 4 zones are not present in totality. If a fault happens, weathering out, suppose that's the one block has weathered out, so maybe completely only 1 or 2 of these are present, rest are gone. So that is also possible. The whole sequence may be drifted, they may not be in situ. So all these possibilities are there. As you are aware of geological processes, all this can happen. So you have to be very sure that that's why any remote sensing study should be validated by the ground survey. Ground truthing is very much important. On ground, you have to examine, inspect, you have to see they're in situ or no, what is happening with these minerals and all that. So these few examples of what we have done in IIRS in different projects. So here ultimately what we get to know is that what is the zone of alteration. Like here we have known that it's argillic to advanced argillic zone of alteration, and there is a aster image, there is a Hyperion image. All Hyperion image is a hyperspectral image only, where contiguous bands are there. In hundreds of bands are there. These basically, because of their high spectral resolution, it is able to tell you which particular mineral it is. So likewise, we have known these are the varieties of minerals. Here, three graphs you see, because one is your what you get from the image. What is the standard? Another is the standard that is available in USGS spectral library, and another is your third one is your handheld spectrometer, what it is getting you. So all these, if you combine and go for a simple analysis, how similar they are, the scores will tell you that which particular mineral the paragenesis belong to, and where do I stand in terms of understanding the alteration zones. But again, we have to do complementary studies like your ICP-MS or XRD, just to ensure that whatever you are getting from spectra really exists. So they are basically your geochemical analysis, which in confirmation can tell you that no, this particular mineral is having this composition. Similar studies we have done. So again, different bands. From the different bands, we can get to know different minerals, and from different minerals, we can get to know what type of hydrothermal alteration zone it belongs to. Right. There can be some pathfinder elements in this study. We have been engaged with last 5 years, 6 years. We have known that on surface there can be several type of manifestations. In geology, we know that it has to be hidden underneath those mineralized zones. They are never exposed. Be it a hydrothermal altered, or suppose it is a supergene enrichment zone. So they are most of the time they are hidden until unless there exists a kind of open cast mining or something like that. So if it is a hidden one, then we have the remote sensing specialists. They have to only depend upon the surface manifestations of this. So what type of surface manifestation we look out? We look out for the alteration zone that we have discussed in detail. So what type of alteration zone? That is a surface manifestation, surface signatures. Another is that you find some pathfinder elements or pathfinder minerals. So like here we have for copper that we have done in study of Alwar, Rajasthan, we have found that the one particular mineral, malachite, the green color mineral, that appears as a pathfinder element. So that happens, that exists on the surface, and this is this we have characterized from the spectroscopy. So thereby also you can tell that due to presence of this pathfinder element, it's highly possible that underneath we may have this kind of mineralized zone. In addition to those, you should consider multispectral images also. That will let you know the lineation zones, so you can get a lineation density map or other structural features like your axial planar cleavage, axial plane itself. Where does it exist? So they basically why to know that? Because they basically act as zones of weakness. So in turn, they basically happen to be the zone of reactivation and fluid emanation. So if fluid has reactivated and through these zones, weak zones, they come to the surface or close to surface, there are high chances are there that we get some kind of very good surface manifestation. So that's why along with doing this hyperspectral study, it's very much important that you see other features also, like your structural features, structural geological features. This is another study where airborne sensors were engaged, and obviously with airborne sensors my spatial resolution is enhanced, and it's very easier, and detailed characterization of minerals can happen. So with the airborne analysis you can be able to tell which type of solid solution member so you are dealing with. Up to that level you can tell. There's some application studies, application out of spectroscopy, that basically spectroscopy we need to understand that it's a indirect science. So like your orthodox geochemistry, you do not break the sample, do not digest the sample with acid and then make it available for the mass spectrometry. No, we're not doing that. It's a completely, the samples will be safe and you do not even touch it. You get spectra out of it. So it's an indirect study, but these indirect studies also sometimes are able to tell you very beautiful stories. So what is there in the mineral, that especially it can tell. And there are some elements like we have not discussed about potassium, about your sodium. Your spectroscopy generally is silent about this. So what about those cations? They are also present. They can be present. What about the silica? So for silica, we have known that if you consider the emissivity range, not the reflectance, the emissivity spectra, there are several criteria, several bands will happen due to the silica structure, presence of silicon oxygen bond. But suppose if we have rich potassium or rich sodium, so your spectroscopy is unable to comment on that. But it's not that. In some minerals, it is possible that you get associated minerals, and there is a there will be a there will be variation of this. Suppose you get iron or magnesium from spectroscopy, and your potassium varies in proportion, maybe directly proportional, maybe inversely proportional in that. So, and you have few studies of geochemistry. So you know the exact potassium content. So I plot the exact potassium content few studies, and I know the iron content or Mg content. With that, I get a line and I extrapolate these lines to tell what is happening here. So it can be extrapolated. It can act as a proxy, in fact, to tell about, to comment about, to know about the elements which do not show a typical absorption, like potassium, sodium, etc. This is a peculiar study that we have done in close to Run of Kutch. with the aster image only, it shows different varieties of rocks, and not only different varieties of rock. How do I know different varieties of rocks? We simply get to know the minerals, and if I know the mineral, we will get to know about the rock. But here we have seen different, not only different varieties, within the limestone also, the single monolithic unit, there one is rich in glauconite, a green color clay mica group of minerals. So limestone is rich in that. Another is simply fossiliferous limestone. So that is purely calcitic limestone. So both these phases also can be very easily distinguished if you do this kind of study, spectroscopic study. And why to do this kind of study? Because Kutch, in this region, we have seen that it's famous for your cement bearing industries, cement producing industries, and cement basically, for cement grade, to qualify for cement grade limestone, what you have to know, your limestone has to be very much pure. So there should be less iron, less silica. So that's why if you know the boundaries of this, and which zone is basically restricted to get you the fossiliferous pure limestone, you're sure the my further mining has to happen within this range only, not these ranges. So that is the advantage of this. This we have already discussed. Okay, different type of studies. Again, it basically tells you this is the region where we helped GSI to get the existence of copper, detection of copper from remote sensing study, and we helped them to get ideas about where to put drill holes. Like I should end here, and I'll keep a few of my next slides. I've kept that is related to planetary, but I expect that planetary spectroscopy in detail is going to be covered in next few lectures. So I'm not going to discuss in detail about this. So, but I would like to give you a glimpse of what is happening here. So it will be very superficial. Detail you will be having in the next lecture. So Chandrayaan 1 data reflectance spectroscopy we have done, and there are several ways to detect the spectral behavior of the minerals. The beauty in the advantage here in Chandrayaan, is that moon is almost airless. So if it is almost airless, then the sensor is there on board and it's getting spectral signature, suppose, of the surface. So the spectra is, you don't have to do any kind of further analysis. So it's error free. You do not have to do any kind of filtering. So it's already processed data. It can be used, but they may not be true for other planetary bodies. So one way is that we get spectroscopic analysis to characterize minerals. In a very beautiful study by Lee et al., they have told that how the water molecules on lunar surface can be detected directly. So they're the first author who have told about the direct detection of the water from polar regions of moon. Now, another sensor, HiC, basically gave basic idea about the spectroscopy. There 1, 2, 3, 4, 5 regions are there, and the 5 different type of rocks. So plagioclase feldspar rich region, and then iron bearing rock, then highland soil, the lunar highland soils, iron rich rock, and then basically mare soils, so that they may be derived from the mare basalt. So different varieties of rocks can be easily shown and analyzed in your spectroscopic by seeing the spectroscope. This is the region where, look at this region where it basically it's a mare moscoviense region, where people are able to tell that where the division between the lunar mare, the basaltic region, and the anorthositic highland region. So that's why plagioclase was there. So this is the boundary. So the boundary basically tells you that the lunar mare starts from this. Very conspicuous studies. And this is what I was telling. It is able to tell you, if you see the pyroxene quadrilateral, mare serenitatis region, and spectroscopic studies, what you have got from that, you can have this kind of plots to tell you, that will be able to tell you which type of pyroxene they are. High calcium pyroxene, low calcium pyroxene, what type of pyroxene they are. So now please understand, we are not in the simple mineral characterization. we are now already into the solid solution end members of those minerals. Right. Tycho has a beautiful story. It will be told in next classes. So I'm not going to give you a detail of this. So this Tsiolkovsky crater, they are important because they produce some kind of different rocks, altogether different kind of minerals. So please understand, there is a crater, and within this there is a central peak. So central peak also has different kinds of mineral. So troctolite, olivine-rich mineral, basically that has been reported here for the first time. And then by doing simple spectral analysis. So if it is a olivine-rich or plagioclase-rich or high pyroxene or low pyroxene, this all pyroxene, magnesium numbers also, with magnesium numbers also it will be able to get detected by Chandrayaan 1. But Chandrayaan 2, was had similar sensor but with a wider spectral range. So that basically helped a lot, and then that studies are going on, and in next lectures it will be shown that what beyond Chandrayaan 1 has happened. Chandrayaan 2 IIRS sensor, basically imaging infrared spectrometer. So in that you see a bit of thermal region, the infrared thermal region also. And the moment you see the thermal region, the expectations become that you can have a chance of characterizing the tectosilicates also, like your plagioclase feldspar. What type of plagioclase feldspar it is, you will be up to that level, you should be able to tell. And that perhaps helps in getting idea about the petrogenesis, or how the evolution has happened in lunar rocks. So these all are possible. So what are the take-home points? I'm now concluding in next 1-2 slides. The take-home point from this lecture is that reflector spectroscopy can provide a crucial help in mineral species identification. We have understood. We started with the physics behind this, and then we have known how your different surface manifestation process helps to get idea about the species, mineral species identification. It can be complemented by image-bound spectra for development of complete spectral library. So this is another thing. If you want to have a spectral library of your own, so why to use the USGS spectral library? You can have your own spectral library for, suppose, developed for the Indian subcontinent only. And as per my knowledge, there exists this kind of spectral libraries also. Many of them exist here. So we can take help from those. And then while comparing your image spectra or your handheld spectra, so laboratory spectra, you compare it with your own spectral library. So for that, a complete spectral library is what you need to develop. So that also can be done from this reflectance spectroscopy. That will be real help to the society. Then the reflectance spectroscopy helps to get idea about the mineral abundance. It can produce the target maps, and it helps in metallogenesis, the way how the metals are formed. So the moment I know that there has been some signatures of hydrothermal alteration, so my process is fixed now. It has to be hydrothermal process. If I see on ground there are abundance of bosons, so I know there are high chances that it has been generated, mineralization has happened due to your the other process, supergene enrichment. It can be the reflectance spectroscopy can be held, can be used in where relatively unexplored area but potentially enriched in mineralized. So what you have in the you can do a post facto kind of analysis. You consider an area where mining is going on, so you all can see what surface minerals are present there. So you have an idea. You apply your image spectra, image derived spectra there. You do some kind of spectral analysis from your reflectance images, and suppose in nearby areas also you see many potentially enriched area, but they are not unexplored. So you extrapolate these knowledge what you gained here onto that area and try to see if those also become unexplored area, those also become potentially rich or no. So that also can be explored. Then in combination of infrared spectroscopy and emissivity. So what we have discussed here is mainly the visible near infrared spectroscopy. The emissivity spectroscopy is another area of concern, and if I combine these two, So spectra that we get from the thermal region or far infrared region, so thermal infrared region, if we combine this with the near infrared region, so the better characterization happens. So better characterization doesn't happen simply because thermal regions are capable of getting me the quartz or feldspar kind of minerals. So obviously there is the advantage that if you get the thermal spectra, silicon, oxygen properties or abundances can be better explained. So that's why all my tectosilicates, quartz and different varieties of feldspar, for that the thermal region is the best. But if you combine these also, infrared, visible infrared, near infrared and thermal together, it helps in calculation of other minerals, other normally rock forming minerals also in a better way. So suppose we have described the fundamental, the vibrational properties, and vibrational properties for carbonate, hydroxyl, metal oxide, hydroxide bonds, etc. Now they have some fundamentals, some combinations in the VNIA region up to 2.5 region and beyond 2.5 region also. So beyond 2.5 also there will be some characteristic absorptions that is visible, that becomes visible only if I combine, take an integrated study of this. So I raised my voice here. These are the some important publications. I have taken help from those in preparation of this slide. So thank you so much. I take